All right, let's talk about pumps. I know, not the most glamorous topic, but stick with me because the rules that govern them are actually fascinating. We're talking about the affinity laws, and they're at work everywhere, from the water coming out of your tap to massive industrial setups. And to understand them, we're going to start with a question, and the answer is going to surprise you. So, let's set up a little puzzle here. Imagine you're in charge of a big pump, and you think, hey, let's crank up the speed a bit. You'd probably expect everything else, the flow, the power, to go up by a similar amount, right? Makes sense. But that's not what happens. Not even close. The real question we need to ask is, why does just a small bump in a pump speed
lead to, well, this? I mean, look at that. It's a massive, almost ridiculous jump in how much power it's eating up. We're talking a modest 50% increase in speed, and in return, you get a staggering 237.5% increase in the power you need. How on earth is that possible? It feels like it breaks the rules of math, but I promise you, there's a perfectly logical reason for it.
And the answer, the key to this whole mystery, is something called the affinity laws. You can think of them as the secret rulebook for pumps. They tell you exactly how a pump's performance, its flow, its pressure, and of course its power usage, is going to change when you tweak its speed. This is how we're going to solve our puzzle.
All right, let's dive in. The cool thing is, the affinity laws are basically just 3 simple rules. That's it. So let's break them down one by one. Okay, rule number 1 is all about flow. Engineers usually call it Q, and this one is super straightforward, exactly what you'd expect. The relationship is totally direct. So if you double the pump speed, guess what? You double the flow. You jack up the speed by 50%, you get 50% more flow. Easy peasy. It's a perfect one-to-one deal. Next up, rule number 2. This one's about head, which is just a fancy engineering word for the pressure the pump creates. And this is where things start to get a little wild. The relationship isn't direct anymore, it's squared. What does that mean? Well, if you double the speed, the pressure doesn't double, it goes up by 4 times. It quadruples. It changes by the square of whatever you change the speed by.
And that brings us to the third and final law, the big one, the one for power. This is the piece that solves our entire puzzle from the beginning. See, power has a cubed relationship with speed. So get this, if you double a pump's speed, the power it needs doesn't double, it doesn't even quadruple. It goes up by a factor of 8. That's 2 times 2 times 2. This crazy exponential jump is exactly why that small speed increase we talked about has such an insane impact on your energy bill.
So here they are, all 3 rules side by side. You can really see the progression, can't you? It goes from simple and direct to squared to cubed. This little table right here, this is that rule book for pumps we mentioned. Now, let's put it to work with some actual numbers.
Okay, theory is one thing, but let's see how this stuff actually plays out in the real world. We're going to grab an example and put these laws to the test.
So let's say we've got our pump and it's just humming along at a steady 1,000 RPM. At that speed, it's pushing out 20 liters of fluid every second, creating a pressure head of 10 meters, and it's using 5 kilowatts of power. Okay, that's our starting point, our baseline. All right, now we're going to do it. We're going to make that exact change we mentioned at the start. We're cranking the speed up to 1,500 RPM. So that's a speed increase of 1.5 times, or a 50% jump. Now let's see what our new rulebook, the affinity laws, says it's going to happen.
And boom, here's the math in action. First up, flow. We take our original 20 liters per second, we multiply it by our speed change, 1.5, and we get 30 liters per second. Simple, just like the first law said. Next, the head, or pressure. We take the original 10 meters and multiply by 1.5 times squared, which is 2.25, and that gives us a new head of 22.5 meters. And now for the grand finale, power. We take our starting 5 kilowatts and multiply it by 1.5 cubed, which is a hefty 3.375, and what do we get? 16.9 kilowatts. And just like that, our puzzle is solved.
Okay, so the math checks out. But so what? Why does any of this actually matter? Well, let's talk about the huge real-world impact of these super simple rules.
When you put all 3 of these rules together, you really start to see the whole picture. That first rule, for flow, it's great. It's predictable. It means controlling your output is pretty simple. But that second rule, the squared one for pressure, that can be a problem. A tiny speed increase can seriously overpressurize a system, which means more wear and tear on your pipes, your valves, everything. And then there's the third rule, the power law. That's the one that'll get you. That's the budget breaker. It means running a pump just 10% faster than you need to isn't a 10% mistake on your energy bill.
No, it's a 33% jump in power costs. It's like a silent killer for your system's efficiency.
Look, if there's only one thing you take away from all this, let it be this. Even small speed changes can make power demand rise a lot. That is the absolute golden rule here. But think about it. The reverse is also true, and this is where it gets really powerful. By just slightly slowing down a pump using modern controls, you can save a massive amount of energy. We're talking huge savings on your power bill, lower maintenance costs, a smaller carbon footprint, all without really hurting performance that much. Understanding this relationship is everything when it comes to designing an efficient system.
So I'll leave you with this final thought. We've just been talking about one pump, but now I want you to think bigger. Think about the thousands and thousands of pumps that are moving water all around an entire city, right now. Knowing what we now know about that cubed relationship between speed and power, just imagine, how could one tiny system-wide speed adjustment, I'm talking just a couple of percentage points up or down, how could that dramatically change a whole city's energy bill? It's a pretty powerful idea to chew on, right? And it's a perfect example of the hidden physics that are shaping our world every single day. Thanks for watching.